All right. So welcome to the AIA Committee on the Environment May 2023 Digital Design Series, the Oregon Design Awards 2030 winner. Super excited about this. Please remember to mute your mic during the presentation and unmute your mic during the discussion. We suggest you set your camera to speaker view during the presentation. Continuing ed credits are available, so please use your first and last name on the screen. And as a reminder, this is being recorded, so you can watch it later. AIA Oregon's community agreements. We seek a community and culture that is respectful, comfortable, open, curious, inclusive, and kind. Community agreements help us identify concrete ways to create a cohesive and safe place to exchange ideas, enable us to interact more cooperatively, and keep us on track. So if you could take a quick minute to read our community agreements, that would be terrific. Thank you. The AIA DDS today does provide AIA continuing education credits, like I mentioned, so make sure that you have first and last name in your signature profile. And finally, take a moment, if you can, to review the learning objectives for today's presentation. Okay, with that, I'd like to introduce our speakers for the presentation. First of all, it's Mark Fretz, DDS Associate AIA. He is the Interim Co-Director of the Institute for Health in the Built Environment and a Research Assistant Professor in the College of Design at the University of Oregon. As a designer, researcher, and former public health service clinician, Mark synthesizes diverse experience to facilitate knowledge exchange between the Institute's industry, consortium, Build Health, research labs, collaborators, and stakeholders. His research interests are focused on exploring and designing synergies that optimize human occupant health while reducing energy use in buildings. An important theme in this exploration is understanding how human migration from outdoor to indoor dwelling has impacted evolutionary mechanisms connected with health and how architectural design can restore these relationships. Josh Richards, PE, SE, is a principal structural engineer with KPFF and has been with the firm since 2003. He is motivated by the demands for constant learning in structural engineering to stay on the leading edge as codes change, new materials emerge, and technologies evolve. Working for over 25 years with various clients, projects, locations, and materials has helped Josh keep tabs on the pulse of the industry and shape creative solutions. His diverse experience and attention to detail give him a well-rounded approach to deliver designs that provide durability, flexibility, and fit tight project budgets, I should say. Jeremy Taves, electrical engineer with Glumac, is another one of our speakers with a degree in renewable energy engineering and a focus on sustainability. Jeremy brings a unique perspective to electrical design. As an electrical engineer, Jeremy has experience designing electrical distribution systems for a broad range of building and occupant types, including commercial, office, education, data centers, healthcare, and multifamily residential. Jeremy enjoys challenging and progressive projects where thoughtful collaboration allows for design solutions that meet client financial, occupant, and environmental goals. Hanbo, AIA Associate Principal at GBD Architects, is a designer and envelope expert with over 22 years of experience in the field of architecture and building design at GBD. He has a deep passion for creating functional and sustainable design. He is known for his innovative and creative approach to architectural design. Han's expertise lies in envelope design, which encompasses the design of the building's exterior. He is well-versed in the latest technologies and materials used in envelope design, and he constantly pushes the boundaries of what is possible in terms of energy efficiency. sustainability, and aesthetics. Throughout his career, Han has successfully completed numerous high-profile projects ranging from commercial buildings to residential complexes. His portfolio includes some of Portland's most well-known buildings, a diverse range of projects including Hassalo on 8th apartment buildings, Multnomah Athletic Club, OHSU, Portland Community College, and more relevantly, the innovative Oregon State Treasury. In addition to his design expertise, he also serves as a mentor to young architects in the firm, nurturing the next generation of design professionals and promoting the advancement of the architectural field. Han holds an unwavering commitment to excellence in design and innovation. His passion for pushing the boundaries of architectural design and expertise in envelope design make him a trusted and sought-after team member at GVD. Jeremy Taves, electrical engineer, Glumac. Oh, I already mentioned him. Thank you so much. Finally, Alec Mahik will be helping out with the Q&A at the end of the presentation. So with that, I will hand it over to the team. Thanks everyone for joining in.
Terrific, thank you. 1 second while I just adjust my screen. Okay, can you see that okay?
Yes.
Perfect. All right. Well, good afternoon, everyone. It's really a pleasure to be with you here virtually and on behalf of the University of Oregon and the Energy Studies and Buildings Lab, which has been focused on creating more sustainable and resilient buildings for over 4 decades. This lab has been receiving support from the utilities since the 1970s to train generations of future architects on how to design higher performance buildings. And in 2002, it became part of the Integrated Design Lab network with the Northwest Energy Efficiency Alliance, which is also known by their acronym NEA. And as part of the IDL network, it's been working through the Better Bricks program to develop holistic and architectural solutions to building energy efficiency. So I would like to acknowledge and thank NEA for their historical, current, and future support of training emerging architects and facilitating industry design consultation at the university to make this work possible. I would also like to thank AIA Oregon for creating a forum to share this and other great work happening in the state. I'll begin with the reporting methods. And if you have any questions as I go through these, please hold those until the very end, during which time we can answer all of the questions. And my colleague, Alan Mahich, is here as well to help answer those questions. So this is a breakdown of reporting methods for energy performance that was used for building emission calculations. And red represents projects that didn't go beyond energy code. Blue represents projects that submitted an energy model. And green represents projects that submitted actual energy use from energy bills this year. Of course, we prefer energy models or energy use from bills whenever possible and available. Sorry, you're not seeing those change, are you?
No, we were not.
All right, 1 second. I'm going to try this again with the sharing. Let's try. Okay, so can you see that?
Yes.
Okay, so that is the breakdown of projects from this past year. Again, green represents the projects that had energy and energy bills and energy models, and blue represents those that submitted just an energy model, and red represents projects that didn't go beyond energy code. Okay, so this year we have 2 standout projects that met the overall 2030 challenge with net positive performance, reporting 106% and 102% CO2 emissions reduction. These 2 projects are both very ambitious and should be commended for the achievements they've made. There were 18 total submissions, and the total emissions reduction from all projects combined came out to 10,340 tons of carbon dioxide across the 18 projects. 6 total projects meet the 2030 challenge for their respective 2015 and 2020 levels. 2 projects were built to and meet the 2020 challenge level, which is 80% reduction. while also meeting the 2030 level, 100% reduction net positive. 4 projects were built to and meet the 2015 challenge level, which is 70% reduction. The total area of the 6 projects that met their respective 2030 challenge levels was just above 1 million square feet, which is about 40% of the total building area across all submissions. This represents very impactful work occurring in the Pacific Northwest. A quick check of the 2030 pulse for our region. These numbers are the average CO2 reductions binned by performance and compared to CBEC's baselines or calculated baselines via tools like the Zero tool. Average CO2 reduction from all submissions is 56%. Average CO2 reduction from the 6 projects that met their respective 2030 challenge level is 87%. An average CO2 reduction from the projects that do not meet the 2030 challenge is still at 41%. Based on these calculations, the winning project, which you'll hear more about today, is a 2-story office building that is targeting net zero energy. It is a resilient design that will serve the Oregon Treasury Department's mission to be fully functional during and after a catastrophic event. The facility was designed to be a low energy building with an EOI of 26.9, and after energy offset from the on-site PV array, the project is anticipated to reach net zero energy on an annual basis. In addition to net zero energy, the facility has achieved a platinum rating from the U.S. Resiliency Council, which is the highest rating possible and the first building in the country to receive this distinction for base isolation. In terms of energy modeling, the project went through an extensive modeling effort to identify a multitude of solutions to make the building structurally and operationally resilient. Some of the strategies and design features include a microgrid controller and energy management system to optimize building performance and resource utilization. So we would like to give a warm congratulations to the GBD Architects Project team, and I'm going to hand it over now to see more about that project.
Great, thanks, Mark, and thanks, Elisa, for the intros. Excited to be here today and present to AIA. Let me get my screen up here. Okay, assume everybody's seen that. Yeah, so kicking off today, a structural engineer. Excited again to be talking about this project that we just completed down in Salem. It's a first of many, and pretty special project to us relative to resiliency. Sustainability and resiliency are 2 words that are used quite often in building design, but they're not the same, and they can't be used interchangeably. One thing that I like to spin on the resiliency with regards to sustainability is really when we look at where we are in the Pacific Northwest and the hazards that we have, specifically earthquakes. And, while these types of buildings might take a little bit more material to build, which is counter to some sustainability goals. At the end of the day, if we do have a major event, which a lot of people are predicting the next 50 to 100 years, tearing down a building and starting over from scratch, obviously is a huge drain on materiality and resources. And so the more buildings we can design to remain functional and undamaged during a large seismic event, I think goes a long way in that discussion. So I'm going to provide a brief overview. These are the learning objectives, which I believe were already up, and as far as what we're going to talk about today. And I'm going to go through this quickly because we have a lot of material to cover. And so if you have any questions, we can answer those at the end. First, I want to just talk a little bit about why buildings make sense for owners. Obviously they resist the disasters, as I just talked about, but when you look at business continuity and sustainable practices that result in less costs to operate, that makes a big difference. These are huge investments in our society, especially with construction costs where they are today. And so owners that are spending all these dollars on structures don't want to just throw that away if we do have a major event. So certainly a lot of pros with resilient buildings, but one big con is that they do cost more to go through all this. We're trying to make inroads relative to making these more affordable, but at the end of the day, there is a premium. What are the types of users are going to use these? So we look at essential facilities as the term that's used in the building code that provide a higher factor against damage and safety. Essential facilities are hospitals, fire, and those types of structures. But what we've done here is we've really gone above and beyond just what a code building requires. I'll hit on that here in a few minutes. But we've actually targeted an exact performance for this structure through the use of base isolation to remain completely operational, limiting damage not only to the structure, but more importantly to the non-structural pieces of the building. And why the Oregon State Treasury? It's a question that comes up. Why would the Treasury need a resilient building? And there's lots of reasons, a few of which are outlined here. But most importantly, I think if we do have a major seismic event here in the Pacific Northwest, those emergency dollars are going to need to be distributed to the people that need them most. And the Treasury is a huge part of that. And so that's one thing I don't think a lot of people think of top of mind when you think about people in need after a large major environmental event. As Mark mentioned, the Oregon State Treasury building, it's a 36,000 square foot office building, and it's designed to withstand disruptions from all hazards, but most importantly, the Cascadia subduction zone earthquake at a 9.0 Richter scale magnitude. We started this project with the team in 2019 and finished in 2022. KPFF and Glumac were actually involved before the actual design team selection in helping the owner kind of build the resiliency goals along with WSP in that process. So what makes a building resilient? If you look at the true definition, it's really the capacity to recover from tough events or outside factors, and threats and hazards are included in that. Earth, Wind, and Fire, great band from the 70s. Obviously those are big ones that affect our community now. Floods and pandemics have also been something that has been more top of mind. The other thing that's not mentioned in here is human threats. We're designing buildings now to deal with terrorism and other things that also play into the resiliency discussion. So some of the strategies to incorporate into these types of projects, obviously the ability to survive and withstand these environmental events, having the independence of energy and that sustainability is also critical, along with health and wellness. Generally, you can design a building to be completely operational after event, but if the energy and the water and the utilities that have going to it can't get there, then you're limited. And so these types of projects do have that independence kind of built in for certain time limits to keep that operation going. So I'll talk a little bit here about the structure, and then I'll pass it on to Jeremy and then Han to talk about electrical, mechanical, and architectural resiliency. But for the structure and for KPFF on this, it was really about base isolation. That was really kind of the key metric for that. We all know what the big hazard here is that I mentioned, the Cascadia subduction zone right off of the coast. I'm assuming most everybody has read or heard, all of the things that could and potentially will happen at some point in our lifetime or our kids' lifetime. relative to this event. This is a graph that I like to show that just kind of references, what really is an operational building and how does it relate to an essential facility and how does it relate to a code minimum building. A lot of lay persons think that if my building is designed per code, then it's going to be fine during an earthquake, when in reality, it's really targeted to survive the earthquake, survive the lives inside of the structure, but generally could need to be torn down or have extensive renovations and repair after that event. And so what you have in this graph here is on the far left, you have recovery time, which is a little harder to quantify. But then going to the right, you have the performance state, which is, what do you want out of that building after an event? And it goes from, keeping it upright all the way to completely operational. Relative construction cost plays into it. But then on the right side here, going to seismic hazard. And there's different levels of earthquakes that the code prescribes, and they're not based on Richter scale. They're based on probability of occurrence. And so the one that we're generally, the big one that we're designing for is what they call the maximum considered earthquake. It's an event that would happen every 2,500 years. The design basis earthquake is a slight reduction from that, and is an event that would generally occur every 500 years. And this really just kind of connects the dots between that performance state and the seismic hazard, crossing over what you're probably looking at based on construction costs. Here's a nice cross section of the office building for Treasury, kind of showing a blown up diagram of the lead rubber bearing isolator, which is the primary isolator, used in the project. But some other things, relative to the architecture is, looking at a lightweight structure. You're not going to typically use a precast concrete cladding on a building that's base isolated. We use the exposed structure to limit how many finishes were on there and things that could possibly need minor repair. Also, you can see the structure and see if there was any damage or anything that's not functioning properly. We used a braced frame for this, also utilized moment frames in the other direction, limited how many, kind of hanging non-structural elements that we had. And then lastly, these base isolators all have to be protected over the life of the building. And so generally they are contained in what we call kind of a moat that is dry and generally unconditioned. This is a photo of just deflection and the actual, movement of these isolators. The building that we did was designed to move up to 18 inches in all directions. Also working on a base isolated building right now that is designed to move up to 24 inches. So generally somewhere between that 6 to 24, 30, even 30 inches is how much you can expect a building to move under the maximum considered earthquake. This is a quick little video here I'm going to show of an isolator testing. When you do a base isolated building, you are dialing in these isolators to the exact friction that they're going to see. And so every isolator occurs under a column, and those column loads are all different, and so, this is where being conservative doesn't pay off in any way, shape, or form, because you don't want to overestimate how much weight is going to be on the isolator. The isolator manufacturer that's selected during design actually goes through a testing program before providing them to the site that tests every single isolator to the exact load that it's going to see. And so we know exactly how much friction is built in. And this is just a quick video of the test. And I should note that this test puts the isolator on its side. So it's 90 degrees rotated from how it's going to act. And that's so they can get the actual load compressed onto the system. And so that really just kind of shows the isolator moving over that whole distance under the compression force that it's seen. And so these were all performed by a dynamic isolation system down in Reno, Nevada. This is kind of a close-up of the actual construction, showing the structural steel frame and the finished product, and the isolators that we had. We had two types of isolators, the lead rubber base isolator in the lower right there that was being tested just now. They also have what they call a sliding isolator, which is kind of a it's basically a disc with a Teflon coating with another piece on top. And really what dictates which isolator is used is the force and the displacement that each one has on it. It's also important to talk about the non-structural performance. As I mentioned earlier, there's a lot of little nuances that go into this type of building. These two photos are from the moat and just kind of show some of the electrical and piping connections that are required with flex connections and what we call loops. So this building can actually move up to 18 inches in all directions without binding any of these surfaces up. Again, you know, one or two breaks in these systems then will affect the operation of the building afterwards. And then I also wanted to just kind of show some testing here of
in Peru, recorded at Ica Station.
And I'm going to turn the sound off for this, but this basically is a shake table in San Diego. I believe they have an 8-story mass timber building on this thing right now. This is a few years ago, and it just kind of shows on the left and the right, base isolation on the left, rigid base on the right, you know, how much more gentle the movement is. I think what's a little more telling here, and this is the photo I showed earlier of the displacement. I'm going to skip ahead here. I think what's telling here is they set up a hospital room in this test to kind of show here, you know, how much damage that you could see. And if you look on the left, it barely moves under the base isolation. It's real slow. On the right, you know, the operating gurney tips over, a lot more shaky than that. So that's kind of a lot more telling in how those different buildings are going to perform. I really quickly want to talk about the USRC. Mark mentioned that we got a platinum rating for the Resiliency Council. This is a similar rating to LEED, but requires a lot more structural analysis, you know, and incorporates everything from the structure to the curtain wall to the skin that you're using to the partitions, and everything goes into this evaluation. It looks at three things. It looks at safety, damage, and recovery. Safety and damage are pretty easy to quantify. Recovery is a little more challenging, but there are a lot of metrics in the USRC design process that evaluates that. You get from 1 to 5 stars for all of these, and our building got 5 stars for everyone and got the platinum rating. So a couple first, again, that Mark touched on. It's the first USRC platinum rated building in Oregon. It was the first seismically base isolated building to achieve this in the United States. And there's only, at the time of the rating of this, there was only 67 buildings in the world that had this. So we hope to see more USRC rated buildings in the future. So with that, I'll turn it over to Jeremy. Yeah, he'll talk a little bit here about mostly, I think, the electrical and efficiency in this building.
Thanks, Josh.
Yep.
Yeah, so in terms of energy efficiency, for the design of resilient buildings, it's more than just looking at a focus on reducing energy consumption. Resilient buildings really require a high level of synergy between both the systems that are consuming the energy as well as the systems that are producing the energy. Distributed energy resources, or DERs, need to be sized in alignment with the project building loads. And a microgrid controller needs to be able to monitor and control all the distributed energy resources and loads in real time. On the Glumac, on the Oregon State Treasury building, Glumac's focus was the mechanical, electrical, and plumbing systems. And on this slide, just highlighting a few of the key systems that we included to support resiliency. We provided the 100% outside air, along with separate heating and cooling systems, a microgrid that we'll talk more about in a little bit, as well as a septic tank and wall systems. And the building included several architecturally coordinated passive design strategies, including a central stair that you can see here that supported natural ventilation. Next slide, Josh. One of the most interesting topics of discussion for this project, next one. Yeah, is really the discussion regarding the difference between a net zero or net positive project and a resilient or grid independent project. It's a lot more involved to design a resilient project compared to a net zero project because you need to have a level of grid independence. So on this chart here on the left, we can see how solar production throughout the day, it's pretty intuitive. There's going to be more sun produced. And then in the evening and nighttime, early morning, you're going to have more building load than solar production. And so for grid tied net zero projects, that's not going to be an issue because you're able to use the utility as an energy bank that you can draw from when you're not producing power. But on resilient buildings that are looking at being grid independent, you really need to have another source of energy storage to rely on during the times when your energy systems aren't available to produce power, yet your building is consuming energy. The graph on the right shows kind of not just from a day perspective like the one on the left, but over the course of the year that energy production on average also is going to be lower in the winter. And oftentimes your energy consumption is going to exceed your production. So not just from an energy storage standpoint, but also from an energy production standpoint, you're going to really need to be considering what type of energy sources you're incorporating onto your resilient building that allows you to be grid independent throughout the year. So next slide. Resilient buildings also have another challenge in the demand and energy use at extremes. In terms of the worst times of the year, may not necessarily be reflected when you're looking at them compared to the annual energy consumption. So looking at kind of three different mechanical systems that were evaluated on this project, a VAB system, which is one that you might see in many buildings today, is going to have a lower energy performance. The DOAS system with VRF is oftentimes employed on more energy efficient buildings today. Benefits from a heat pump technology. It typically has a coefficient of performance of 2 or greater, which reduces the demand. And this is the system that was employed at the Oregon State Treasury building. And then the system on the right is a DOAS with a ground source heat pump, has a heat exchange with the ground and is able to be more efficient because in the wintertime, you're going to be bringing up heat from the earth. But for obvious reasons that we just looked at with Josh and our desire to be isolated from the earth, that was not really a good option for us. So the chart on the right here kind of shows how the annual energy use for the same systems, or rather what's interesting about the chart on the right is that the energy benefit of the more efficient systems annually averaged is only about 20% better than the worst case system. However, when you're looking at the worst case day, so in the middle of the winter for heating dominant zones like ours, that delta between the different systems can be 60% more efficient for the more efficient system. So where this comes into play with resilient buildings is when you're sizing your energy systems to support the building loads, not just from wanting to be net zero over the course of the year, but rather being able to support your building loads in real time on that worst case day. Next slide, Josh. And then another key focus for resilient buildings beyond just system selections is to ensure that they remain resilient as the building owners adjust operations over time. So to achieve that, we want to make sure that there's an energy management system in place to monitor how energy use changes over time. And at the Treasury building, we're using Copper Tree Analytics, which is a third-party measurement and verification company that provides continued support and monitoring of how the building is performing. Next slide. So we talked about how resilient buildings use energy, and now what we needed to do was really design a system that was capable of providing resilient power to meet that demand. So using a series of different modeling software that evaluated microgrid technologies, we're able to bring in or import energy modeling data associated with our building and evaluate different technologies, solar, battery, generators, to determine what mix of distributed energy resource systems would be most appropriate to meet the goals of the project and what size each of those systems should be. Next slide, Josh. So once we kind of worked through general system sizing from an energy standpoint, we were able to collaborate as a design team to provide space planning and figure out exactly where all of these components that we were going to be including on the project would live and how they would interact with each other to meet the operational intent and system functionality that the Treasury was looking for. Next slide. One interesting thing about microgrids is that they can really provide a range of different modes of operation. For the Treasury project, specifically was focused on resiliency and providing backup energy systems that are always on standby to provide the maximum amount of operational runtime in the event of a disaster. So that said, the microgrid controller also has the ability to allow the building to operate in a range of different operational modes in the future, should they choose to look for different options. Some of those options would be emissions reductions, demand management, or optimizing for financial payback. And it's important to remember and convey to the owner that these systems are very complicated, and facilities group, in order to operate and maintain them, need to be provided with ongoing training and support. And so we've partnered with Schneider Electric as the company that provided the microgrid and is providing ongoing training and support as needed. Next slide. So in terms of the components that were included for the microgrid at the Oregon State Treasury building, we have a solar PV system, 238 kW. We have a battery energy storage system, it's 250 kilowatts, as well as a diesel generator, it's 300 kilowatts. And one of the greatest things that I guess provides the most significant value for the Treasury in terms of having a microgrid with multiple overlapping distributed energy resources is that not only does an owner get the benefit of having these redundant systems, if one were to go out, they have another backup system on hand on site, but the microgrid controller enables all the distributed energy resources to operate as a collective. And as such, the runtimes are compounded in an optimized fashion rather than just stacking one after the other. So you don't just get a 1 + 1 = 2 scenario where you have a 96-hour fuel tank for the generator and a 1 hour or 2 hour runtime for the battery. By using them in an optimized or programming them such that if the generator is burning fuel in a less efficient manner, it can burn fuel more efficiently and charge the battery. So you're able to really kind of marry these technologies together and have them provide as long of a runtime in this case as possible. So that's what this graph in the lower left-hand corner is showing. Next slide. One of the important considerations to be aware of when incorporating a microgrid pertains to the transitions between different power sources. And in general, microgrid components are going to require what's called an open transition or a break before make transition. Open transitions result in momentary power blips on the order of a few milliseconds, but many systems like motors and heaters are going to ride through these blips without any issue. But other more sensitive electronic equipment, computers, controllers, server rooms, AV equipment, etc., they're going to want to have some sort of backup power system, a UPS or other integral battery backup, to allow them to not go through a reset process if they're part of the critical operations of a facility. And final slide. So yes, we've covered quite a bit in just over 10 minutes. but hopefully it gives a brief snapshot of some of the systems electrically and mechanically at the Treasury building. Obviously, it was a great project to be part of, and have a whole lot more to share if the time allowed, but always open to sharing more at another time. And the final thing that I wanted to highlight is that by focusing on resilient buildings, it's made net zero easier and achieved also a lot of secondary benefits as well. So in addition to reducing energy use, providing optimized system operations, potential to be net zero, and it also contributes to the greater resiliency of the utility grid by reducing the peaks and valleys of demand, and allows the grid to become less carbon intensive because they're not having to maintain as many spinning reserves of carbon intensive energy sources. So a lot of benefits to incorporating resilient building approaches on projects looking forward. So at this point, I'm going to hand it off to Juan. And thanks, everyone.
Thank you, Jeremy. Another key strategy is a building that is sustainable. A building that minimizes the impacts on the environment, meet sustainability benchmarks, support the resilient design. These requirements are typically very prescriptive, and today we don't have the time to go to the level of detail of that. Next, John. Unlike sustainability, the health and wellness aspects of the design is more subjective and more like the ambiguous gray area. It's hard to put a number on. Next. This image gives you the ideas of the design evolution. The design concept is to withstand and connect to nature. The base isolation had a major influence in our design. We have to keep the massing as simple as possible, minimize number of corner in and out. So that's how we start out with the simple mass. And then, again, we designed the building from inside out. So we organize the massing by the uses, and then articulate to reflect the interior, the space layout. Next. Again, we design the building from the inside out. And at the end of the day, it's all about the human using the space. The simple floor plans divide into zone. That the central zone is a circulation, meeting spaces, all the support uses, and the outside is the open, flexible office space that maximize the use of nature, actually use of natural light. Next. Again, articulating the mass. The idea is that the slip and slide the massing on second floor, east-west direction, allow us to maximize the view to nature, and also allow for abundance of fresh air, natural light, while still control the sun glare. As well as break down the overall mass into human scale. We also bring biophilic design element into the building by incorporating green wall, preserved moss, warm white oak wood panel into the building. Next. Here are the rendering of the overall project with feature of the resilience that Josh and Jerry were talking about. Next. In recap, the resilient structure, energy independence, sustainability, health, and wellness that make resilient building, we call it a super building. Next. Here are a couple quick perspective views sections that show the way that we treat in the interior space with natural light, vertical circulation to connecting all the floor together with a green wall and open wood glass stair. Next. Here's the final images of the project here. This is the view from the northwest east corner. You see the entry plaza, the tall windows on the north side, the animated aluminum panel wrap on the sides of the building, and the flat metal panel on the end, at the end, it kind of mimic the tree trunk that lay on site. Next. This is a view at the east elevation, so the main entry corten steel structure. Also, the ribbon design that actually accentuate the roof cantilever to provide shading and protecting the balcony and entry below. Next. This is a view at the southeast corner, and we slope the south wall and step in the building back a bit on the lower level to allow the skin that's shading the window and reduce the sun glare. Next. Here another view at the northwest corner, continue with that ribbon design concept that's similar to the east side, that essentially the roof form that cantilever out from the building to maximize roof area for PV panel. Next. Here's a view at the interior. We bring in the biophilic design, integrate the green wall and warm whitewood panel into interior. Next. Here's a view at the atrium. You can see open wood glass stair with clear story above, bring more natural light into the space. And also you see the green wall that run 2-story height. Next. Here's a view at the break room. The furniture was manufactured by the Oregon Correction Enterprise. They train in inmates to prepare them for societal re-entry with professional experience, which is really cool. Next. So this is view at the large conference room. This conference room can divide into 3 smaller meeting spaces that is allowed the public to use. Next. Here's a view at the second stair. The mural is painted by the local Native American artist. And the picture on the right, you can see that the central core office building on the left with wood cladding, the walls go partial height, allow the light on the north side penetrate further deep into interior spaces. I think that's his last slide. Thank you. We open for a question now.
Yeah, I think that's all we have. So yeah, welcome to answer any questions or.
Thank you guys, it was a great presentation. So yeah, everyone, if you want to go ahead and turn your cameras and mics on, you're welcome to ask questions, or feel free to put any questions in the chat box too.
Does the base isolation system allow for vertical movement of the building also?
It generally, there is some vertical movement built in, but it's not, it's less than an inch. It's not, generally you're subject to just the lateral movement only, but you are limited to how much uplift loads can be transferred through the isolation. So you're not expected to see damage from any vertical accelerations.
Thank you.
I think you're muted, Elise.
Thank you. If each base isolator is this question for you, Josh. If each
Yeah.
base isolator is designed to pick up distinct loads associated with each column, is there direction to the client to avoid changing loading at all? You know, let's say there was some additional high density storage or something that had to come in that would change. Is there kind of a factor of safety where they could do that kind of work? Or do they really have to understand the system and leave it alone?
It's a great question, Lisa. We did talk to the Treasury about that. Yeah, I mean, you are, you know, if you're going to substantially change the loading criteria, then you would have to look at the isolator design. There is some there's some flexibility built into the design. If you know, there's always plus or minus, because you know the hardest thing to estimate is live load. You know, an office might be designed for 50 pounds a square foot live load, but does it really see that? And so there is some inherent flexibility built in. But if you were going to change a whole section of this building to a high density storage, it was really going to see that load, then you would have to incorporate a retrofit into the isolator design as well. Yeah.
Thanks.
So it looks like there's a question in the chat box pertaining to how water was handled. I don't know which one of you can take that, but gray water recycling, rain capture is the question.
Do you want to take that one?
Yeah, why don't you take that one?
So some of the water was reused on site for irrigation. We did have some backup, like resiliency for a well. I mean, there's a well that's being used, but in terms of rainwater harvesting and storage, most of it was irrigated, is my understanding. Is that in line with yours, Juan?
That's correct. I don't think we capture any water for reuse. Most of rainwater are captured and treated on site, and then we have that that pond further closer to the creek that can take care of all the treatment there. But we don't treat the gray water or black water for that matter.
Yeah, no treatment or storage facilities on site. It is worth mentioning that because of the proximity to Mill Creek down there in Salem, there was some flood concern. We actually set the building pad. You can see it's kind of raised up there above the 500-year floodplain. So again, that was an additional resiliency. It was obviously easy to do that with the moat that we had to build in for the base isolator, so we didn't have to excavate down very much to set that. But that is a consideration on other sites. If you got to dig down another 6 feet, it's almost like a partial basement.
Got a question here. Great presentation, everybody. I very much appreciate the clarity of how you broke through this, kind of walk through each of the systems. And yet what I'm really struck by is the elegance of this design. I mean, regardless of all the other things that you've talked about, resiliency and the structural systems, this is a clean, elegant building, and I compliment everybody for that. When I look at this cantilever deck, I'm assuming this wasn't a suggestion by the structural engineer with all the seismic criteria that we're trying to meet here. So Josh, maybe there's some interesting conversation about the design process from the structural and architectural perspective you might want to talk about, but maybe this is a really good example of why focusing on base isolation is so important, because some of these kind of more challenging structural elements are really resolved at the ground that way.
Yeah, it's a good question, and Han alluded to it a little bit earlier about the simplicity. We kind of had a little arm wrestling match. You know, we made him stack all the columns, but in return we had to do some large cantilevers. You know, so you know, certainly the cantilevers, I mean, they were a big challenge because they're, I mean, they're pretty thin, and we had to pack a decent amount of steel in there to get those to work. Those don't really translate. I mean, the building is going to float similar to if you were on water, and so the cantilevers don't really have an adverse effect on that as much as if you had a lot of irregularities, reentrant corners, and transfer columns, and a lot of different things like that. In reality, since the base isolators have a real cost to them, a method to reduce that cost is to have a smaller footprint and then actually utilize cantilevers to a degree. So it's an offset of how much steel tonnage are you looking to get the cantilevers versus the cost of the base isolators. Obviously here that wasn't a huge factor based on it not being a real large building, but certainly it was a major design feature. Colin can elaborate on that, but
Yeah, it is a design feature for the building. Of course, structure and architecture, we always fight on this kind of stuff. Structure want to be, large size of beam, a couple of feet tall, but we try to keep it as minimal as much as we can. The reason for this is that because we couldn't do it much on the ground floor because, we minimize the corner that integrate with the mold, so 18 inches all around, that's a challenge for us. So the only thing we could do is the second floor, right? It's a freedom to express what we can because nothing to do with the mold below. So it's allow us to express the design and extend the building further out to maximize the PV panel. That's not an element we need to capture more electricity as much as we can. And also using the design to seal the thing in the background, for example, entry plaza, where you had a whole hotel in the back, we try to conceal that by extending the vertical element integrate with the roof and the balcony. Same way with the other cantilever on the other end that extend out, conceal the mechanicals and other thing that we don't like to see.
Thank you.
I was wondering if you could explain the seismic structure that was at the second floor intersection with the first floor. There was a drawing where you had the base isolators, but then also another seismic structural feature that was between the first and second floor.
I think it was really just pointing out the seismic resisting system, which was a brace frame and a combination brace frame and MOMA frame system. There's nothing between the floors that do anything relative to the base isolation. I will say that when you look at, I mean, the term base isolation implies obviously that you're doing it at the bottom, which is generally how it's done. However, there are a lot of examples where the isolation occurs at a higher level or even at the roof. For example, the new concourse or the new terminal at PDX, the roof is base isolated and the isolators are at the top of the columns. And the reason for that is we were trying to limit the loading at the base because of the liquefiable soil and some other geotechnical challenges that we had. So, there's all kinds of reasoning for where you do it. Generally, it is at the base, but on this building, there's no other movement joints at the second level.
Okay, good. That makes sense.
Yeah.
Thanks.
There's also a question in here, it looks like, about open operational windows. That one I can't answer.
Yeah, so
do these windows open?
We do have a upper window almost every single base, and that's the upper window is operated by user, but we do have a motorized upper window at the clear story, allow us to flush out the hot air when we need it.
Well, we are just at time, so if there aren't any more questions.
Yeah, appreciate you guys having us present. I mean, obviously there's a ton of material here, and it had to go kind of fast to get through everything, but certainly willing to, if anybody wants to reach out and have more questions or talk to any of us, totally welcome.
I have to say, I was on a tour of this building, and it was amazing. I thought it was just incredible.
Thank you.
Thank you. Nice job.
Yeah, thank you.
Thanks, everyone.
Thanks.
Thanks.
Yeah.
Well, good evening.
Thanks, everyone.
Yeah, thank you so much.
Thank you.
It was great. Have a great evening. Take care.
You too. Bye-bye.